Hello, my name is Joshua Ellis. I am a master's student who will be graduating this summer at Missouri State University. And today I'll be talking about a project I'm working on, which utilizes um, deep learning algorithms, neural networks, to identify structures within infrared spectra. The project I'm working on essentially takes a FTIR spectra and then tries to identify certain features within a compound. So a compound's structure is what's responsible for these absorbance peaks within the spectrum. The interferences, the interactions between these atoms cause it to absorb light by the way they're bonded together and the way they connect to each other. And then that creates a spectrum of absorbances at various wavelengths. It absorbs varying amounts of light, infrared light, at these wavelengths. So this is the spectrum of this compound, and then different compounds, of course, have different spectrums. So what I'm trying to do is take a neural network, in this case a convolutional neural network, which identifies local patterns within the spectrum, sort of small patterns and patterns on small scales and patterns on large scales, by inputting the spectrum into the network, inputting it as a kind of a 2D image, but a very flat one, and then pulling across this wavelength axis, and pulling it down from 600 to, at this point, it'll be 75 data points wide, and then using a multi-layer perceptron to predict the value of that score. And then that score is just whether or not the feature this network has been trained to look for exists. So, for example, we could say, is this alcohol here? Hydrogen and oxygen is alcohol. So it tries to see if that structure exists within the spectrum, if this spectrum would suggest that that is there. And it gives a score for how likely it thinks that does exist. Anything higher than 0.5 is considered a true. Less than that is considered false. It does not exist. So here we have results from that. These are in error rates. So, and this is error rates for positive samples, so false negatives, and error rates for negative samples, false positives. And carbonyl is a fairly easy one to identify. So we started with that and saw that it can be identified very, very accurately, about 96% accurate. And it presents very well within the spectrum. You'll see a peak right about here, or right about here on this one. Very tall peak there, so this one shows it pretty easily. But then we try to figure out if we can detect things from adjacent to that. So next to this carbonyl structure, is there carbon? Is there chlorine? Is there hydrogen? Is there these? And then we have one going off both sides. So carbon has two bonds coming off of it usually. So is there carbon on both sides? Is there carbon and chlorine? Is there carbon and hydrogen, etc.? And then these are different structures that are not based on carbonyl. I mean, we have carbonyl again, but then we have double bonded carbon, triple bonded carbon. These are certain alkyl structures and various others. One of the results that has been seen from this is that generally, certain structures have a little bit of trouble because they just don't present very well in the spectrum. The alkyl structures are generally considered less important for what the compound does. But more prominently, we see that if there's just not enough samples of something, or in this case, not enough counterexamples, because this is almost all the data set has these in it, concerning the organic compounds, that then these will not show up very well. But otherwise, it's mostly just a matter of having enough data. And you can sort of see that trend here. If there is enough data, you can get a lot of times close to 90% accuracy, which isn't perfect, but for identifying every single part of the structure potentially, it shows that this method is viable with enough data, that you can really start to piece together the different parts of the structure and figure out what it is. And so in the future, I would like to expand on that and figure out how we'll get a larger set of structures, of just as many structures as I can by going to the data set, and then begin to piece back the full structure of the compound.